Max and multi-max is a typical product mix problem. Here we will summarize the basic features for such type of problem. In product mix problem, you need to decide how many to produce for each product, given the limited resources. Decision variables are the product quantity. Typical objective is to maximize the total profit. Besides the resource constraints, other common conditions to consider include demand and market requirements. A variant of a product mix problem is called make or buy problem. Still, you need to decide the quantities for different products. However, the key difference here is that there are more than one sources for you to obtain a product. Hence, we need to determine how many to obtain for that product from each source. For instance, if a product can be either made or bought, then for this product, we need to know how many to be made and how many to be bought. Depending on the problem setting, we can have two different objectives. If a specific product mix is given, that is, we know in total each product how many is needed, we can try to figure out how to distribute among the sources so that the total incurred cost is the lowest. If we don't know the product mix, then we typically need to maximize the total profit. The typical constraints include resource, demand, and some limitations on the sources. Okay, let's look at the example of this Electropoly Corporation. This is a typical buy and make type of question. We know $750,000 order must be received from all the three models. We know the product mix, how many must be ordered for each model. The resource uses data and capacities. There are two sources to obtain each model. We know their corresponding cost. Since we know the product mix, our objective is to find a way to get that specific mix at the lowest cost. As the decision variables, we need to know how many to buy and how many to make for each model. Since each model has two sources to obtain, this results in 6 decision variables. If a model can only be bought or only be made, then for that model, one of the 2 decision variables is a dummy variable. You have to force it equal to 0 in the constraint. Here is the objective function, calculating the total cost based on the decision variables. It must be minimized. We have 3 types of constraints. One is a demand constraint. It ensures the quantity from making and from buying equal to the specified product mix. 2. Resource constraints. This is for making the products, so only making quantity decision variables are used here. The last one is the non-negative condition. Now, we have formulated the linear programming for this make or buy problem. And next, we will move to the Excel. We are going to see how it is set up in Excel and how to use solver to get the solution. Now, let me show you how should we complete this spreadsheet model for the make-buy examples. So again, in these blue areas, I put the known information. So all the parameters we got from the problem setting. All right, so we need to specify three group of things. First is what is the decisions. We need to specify our changing cell. So we have in total 6 decision variables. So the changing, we need to specify 6 changing cells. Then the second group thing, we need to specify the constraints. So we have the capacity constraint, demand constraint, and the boundary constraint. So capacity constraint is only for the in-house making. So it's only involve number to make those decision variables. It's related to 2 resources. One is wiring capacity, the other is harnessing capacities. So how many wiring and harnessing capacity are available? Actually, we have that information. So wiring is 10,000, harnessing is 5,000. So what we need to do here, we just say those 2 is equal to, we just refer to the given information. So we input, these are the available resource. Then the important thing is we need to calculate the consumed. Available resource will be no less than the consumed. Consumed is based on number to make, so number made for each models. Then also based on the hours you need for each unit for wiring and for harnessing. So the consumed wiring capacity will equal, we're using some product function. So we will call in this changing cells just for number to make, and then some product with hours of wiring per unit. So this is consumed. Since we got 0 is because we don't put any number in the decision. So you can actually, we put, let's try, give a test number. So let's suppose number to produce for each model is 1 unit, and the number to buy for each model is also 1 unit. Okay, it's easy to check. Okay, this is 2 hours, model 1, 1.5, model 2, and 3 hours, model 3. Plus them together is 6.5. Okay. All right, now same thing for the capacity. So we need to sum product. Now again is what we made in-house, that group of decision, and some product with the hours of harnessing per unit. All right, so then we will know this how many is consumed based on our number to make for each model. Now, second constraint is a demand constraint. We want the total numbers we order must equal to the total number we have obtained. So number ordered, we have that information. So number ordered is given. So 3,000 model 1, 2,000 model 2, and 900 model 3. So we will just put that information in this place. All right. So this is number is ordered by the customer, and what we obtain from both sources, making in-house or outsourcing, the total number we got from those 2 sources must satisfy the customer's order. So that means we need to sum up the number for each model, how many we have made, and with how many we have bought. So we just plus them together, and this has to be equal to number ordered. Now, third type of constraint is boundary constraint. We want non-negative every decision variables that will be specified in solver. Finally, we need to calculate the total cost. So total cost will involve all the changing cells and the cost to make associated with the number to make, and the cost to buy associated to number to buy. Those are both cost parameter and the changing cells. They are put in a 2 by 3 range. So we can use the sum product again. So sum product and all the changing cell in this range, sum product with those cost parameters. All right. So that is the total cost if we produce 1 unit for each model and buy 1 unit for each model. Now we are ready to solve this linear programming. So we go to the solver. We need to tell the Excel, okay, what set objective? Objective is total cost. We wanted cost to be minimized, so minimal. What's the changing cell? Changing cell is this green shaded area. Okay, we add the constraint. So first we add constraint. We say, okay, cell reference, that is what we should calculate our consumed capacity. So cell reference, this cannot be larger than the available capacity. So that we add. This is for capacity constraint. Now how about demand? So demand, so our cell reference, so with number obtained must be equal to the number ordered. Then click OK. Now we have those two constraints added, and also we have this box checked. That means we want non-negative. So important thing, so constraint configured, the last thing to indicate is this is a linear programming. So we need to select this simplex LP. So click solve button. All right. Okay, quickly it find the solution. So this is our solution, and you can keep the solver solution, and also you click sensitivity reports. You click the OK button.